Hello, everyone. How are you?
Good, how are you?
I'm doing all right. All right. So let me start with a reminder item here. So tomorrow you have your number 10 homework due. Okay, it's due at 11:55. All right, and then I'll be working on the assignment of homework 11 this afternoon and tomorrow. So I'll post that latest by tomorrow at some point. Okay. Um, Second one here, I'm just wondering if any of you guys want to lab assist physics next semester or the spring semester of next year. Okay, so you can let me know or you can sign up from the email that Cheryl sent out to you guys earlier this morning. Okay, so that's something you can think about on
Um,
helping.
with the with the lab assisting and stuff, I was looking at the email and I got a little confused on like how to sign up for it or something like that. So how would I go about? So just email you and like say that I'm interested.
Yeah, the original email was sent out with a link you guys can put in your names in it. So if it doesn't work, you can yeah, let me know which section you want to lab assist. Then yeah, that will work as well. Okay. So
Okay.
yeah, the process is so probably like if there are more of you guys sign up than the sections we have, then we'll have to decide later like who will get the job, who will not. Okay, so if not, then you will probably get it because at this moment they are so there are four section in fall, four section in the spring. Okay, we only at this moment we only have two in the spring field. Okay, so if you just sign up right now, probably you'll likely get it. Okay.
Okay, so just go to that Excel sheet. Is
Hmm.
that what it is?
Yeah.
Okay, and then do you just like put your name in it?
Right. Hmm.
Oh, okay. Because I thought that's where I kind of got confused. Was I didn't
Uh-huh.
know that we could just like put the lab.
Yeah. Put your name next to the section you want. Okay. And then I think it says so next to your name, you put how many sections you want to lab assist in total. So um, let's scenario like this is for like mostly for biology and chemistry students. So they have options of picking more than say um, two or three sections. So, but they may sign up for three sections, but they may just need to lab assistant two of them. Okay, so then at the end they
Okay.
will be deciding. Okay, all
Okay,
right.
thank you.
Okay, you're welcome. All right, so that's that. If you still have questions, you guys can email me. Okay, so one thing is um, you don't have to know like every details of each lab will be doing, okay, because most of the time the instructor should be also in the lab. Okay, so if you get like one or two um, little things you don't know about it, it should be all right. Okay, so your responsibility should be mainly like setting the lab up and then cleaning up afterward. Okay, and then during the lab answer some questions. Okay, so that would be it. Okay, if you work with me, I think that's pretty much it. Okay, but there's chance you will be working with Dr. Park for the fall semester for the engineering students. Okay, so he might have a little bit different um, say responsibility for you. Okay, but you can also check on him if you want. Okay, all right, so we'll get started here on today's lecture. This is um, about section 17.5. Okay, so we'll be looking at general plane motions for an object. Okay, so we'll start with again reading quiz and then briefly going through the equation of motions and then on the problems with friction involved. Okay, and then quizzes and then group problem solving. Okay, again let's start with the reading quizzes. So this is for extra credit again. Okay, send me your answers in the chat privately. Okay, so go ahead and do that. All right, so I think I have everyone reply to me. So let's take a look here. On the first one, it says if a disk rolls on a rough surface without slipping, the oscillation of the center of gravity will, okay, so if no slipping, then it will be equal to alpha times R. Okay, so either B or C. Now the friction force will be, so if no slipping, then the friction force should be static friction. Okay, static friction always have a magnitude of less than mu s times m. Okay, so it's going to be C here, right? So remember, if there's no slipping, then it's static friction. Okay. On the second one here, it says if a rigid body experiences general plane motion, the sum of the moments of external forces acting on the body about any point P is equal to. So if you take an exit going through point P, then the sum of moments should be equal to the moment of inertia about point P times its angular oscillation. Okay, so option A, that should be this guy. Okay. All right, so then C and A on list two. All right. So let's take a look, quickly look on the lecture of the day. So it's about equation of motions, general plane motion. So if an object is having general plane motion, then it will have translational motion as well as rotational motion. Okay, so then basically we'll be looking at the three equations of motions. For the x component, net force should be equal to m times acceleration in the x direction, and then y component net force is equal to mass times acceleration in y direction. All right, so this two is the translational motion, and then about the rotational motion, it's going to be summation of moment. This is about center of gravity. It's going to be equal to I times center of gravity times alpha. Okay, now in general case, you don't always have the rotational along the center of gravity. So you could have a rotational about the exit going through point P. Okay, so if that's the case, then um, summation of moments, okay, about point P, then it should be equal to IP, the moment of inertia about point P. Okay, about the exit going through point P times the angular oscillation. All right. So if you know the moment of inertia about center of gravity, then simply you can do this is again the parallel exit theorem to figure out the new moment of inertia about another rotational axis. Okay, so you can put this way, or you can do you can look at the kinetic diagram of the body, and so then it would be summation of the from the moments of the kinetic moments about point P. Okay, so either way, either this one or that one. So again, you will have three equations. Okay, all right. The second topic in this section talks about if there's frictional force involved on rolling motion. Okay, so if you have a disk, okay, that is rolling, then there will be friction force involved. Okay, it could be either static friction if the rolling motion is not, if there's no slipping of the disk with the ground. If there's slipping, then you will have kinetic friction. Okay, so you want to be careful about if it's slipping or not. Okay. Then for the equation of motions, if you have a rolling motion, so in this example over here, so if this is the free body diagram, now the friction force is in the backward direction. So if this is the case, then this is indication that the object is rolling with slipping, okay, because then you will have kinetic friction will be in the opposite direction of the motion, okay. Now, if you have static friction, if you have no slipping, then the friction force should be to the right. Okay, so be careful about that, and then how you come up with your free body diagram. Okay, so if this is case on this scenario here, then net force would be this pulling force P minus the kinetic friction. That should be equal to mass times acceleration. Okay, in y direction, net force should be equal to 0 because the motion is not along the y direction. Now, if you take the axis going through the center of the gravity as your rotational axis, okay, then summation of mg equals to ig times alpha. Okay, so you'll have these three equations. Okay, now you probably will have more than 3 unknowns to solve for, because friction force a lot of times could be an unknown as well. Then acceleration A should be could be an unknown. Alpha could be an unknown. Okay, so then there could be additional unknowns. So if that's the case, okay. All right, so F, this is an unknown, N is an unknown, alpha, AG is unknown in this case. Okay, so then now you have three equations. Okay, you probably need one more to solve for all the unknowns. Okay, so there are two scenarios. Okay, so if there's no slipping, all right, then the rotational at the contact point of the object with the ground, okay, that should be having at that particular point the velocity should be 0. Okay, and then we had this already derived previously in chapter 16, that in that case oscillation of the center of gravity should be equal to alpha times r. Okay, so this you can check earlier in the earlier chapters we have. So this can serve as the force equation. All right, do not use this equation, the friction force equal to mu s times m, because this is kinetic friction, or this is static friction. Static friction should be less or equal to this guy at most. Okay, so you don't use this equation, but you can use this equation to be the force equation. All right, because static friction is less than mu m, okay, or equal to mu m. Now, in the second scenario, if there's slipping, okay, then you can use kinetic friction equal to mu k times n as the force equation. But in this case, then Ag is not equal to alpha times r, okay, because there's slipping. Okay, so be careful about which force equation you should pick up. Okay. All right. This is the general procedure for analysis. So first, as usual, we will set up an x and y coordinate system, okay? Because this is a plane motion, so then the motion is either in x or y direction, okay? Or you can always set up x, y to be on the plane of the motion, okay? Now, the second one is, okay, the first step, after you're setting up XY coordinate system, you want to draw the free body diagram and then also the kinetic diagram, okay? The second step is to specify direction and sense of oscillation of the center of mass and the angular oscillation of the body, okay? And if necessary, you want to compute the body's moment of inertia, IG, all right? So step 3 is, if the moment equation is used, then use the kinetic diagram to help visualize the moments developed by the components of MAG, X and Y, and then IG alpha. Okay, so apply those three equations of motions. All right, then identify the unknowns. Okay, so if there's rolling motion, you want to make assumption if there's slipping or no slipping by, then you can establish a force equation. Okay. Now sometimes you might want to use kinetic equations, okay, to complete the solution as necessary. Okay, so that's it depends on problem. If it gives you enough information for you to utilize kinetic equations, then you can do that. Okay, for example, it says, if it says the object oscillates from rest to, say, how many or how much in angular oscillation or in angular velocity in how many seconds, then you can pretty much figure out what's the angular oscillation in that way. Okay. All right. So if less rolling motion with a slip or no slip assumption was made, you can check its availability at the end by checking on, say for the static friction, it should not be greater than mu s times n, okay? And then for kinetic friction, it should be equal to mu km, okay? So that's something you can use to check, okay? All right. So let's have let's take a look on the concept quizzes. Okay, so let me open the breakout rooms for you guys to work on these two problems. Okay, so after you are done, you can come back here. We can check the solution together. Okay, and then we can look on the attention quiz later. Okay, so let me put 3 breakout rooms. Okay, for you guys. All right, now the rooms are open. You can join the rooms. All right, so you're all back, and most of you guys have your responses sent to me. Let's take a look here. The first one here, it says the spool is on a rough surface and a cable exert a 30 Newton load to the right. The friction force at A X to the, okay. So in this case, they actually indicate it's going to be a rough surface, okay? So we are going to just assume that the surface is rough enough, all right? So then it actually doesn't slip, okay? That's our assumption over here. So then if it doesn't slip, then this is static friction, okay? Static friction, in this case, is going to be tricky. It's going to be to the um, right, okay? And you can imagine it this way. Just imagine if you are walking, so then your foot will push forward, backward, right? So the floor will push you forward. So that's static friction. Okay, so this is similar scenario. So at the point of contact, actually the spool will push the floor backward, and then reaction from the floor will push it forward. Okay, so this will be the friction force. Okay, so it will be to the right. Okay, and then AG should be also to the right because the external force is going to the right. Okay, so then it will start to the right. Okay, so that should be the first one, C. Okay, you guys all got this one right. All right. Now on the second one here, so we have these two forces. We should also indicate the other two forces. Okay, so there will be mg. All right, there will be normal force m at this point of contact. Okay, upward in that direction. So then you should have four forces on the spool here. Okay, normal force, the weight, the friction force, the pulling force. All right. Now for kinetic diagram of this spool, okay, so the spool, it will have oscillation to the right, okay, because you are pulling it this way, so then the alpha is going to be in this direction as indicated, okay, by the graph. So then this is the summation of the moment should be I times alpha, okay. So summation of force should be mg, summation of moment should be I times alpha, okay. So then in this case, we are looking for, on the second problem, we are looking for the moment equation about point G, exit going through point G. Okay, so then we are looking at the summation of moment equation about point G. All right, so um, there are four forces here. So for the moments, you should be looking at the free body diagram. Okay, four forces here. The weight goes through the center of gravity, so the weight will have zero moment or zero torque. Okay, so the moment is all, the torque is the moment, okay, of that force. So because it goes through G, so then it's 0 times mg will be 0. Normal force acting at this point also going through this G here, okay? So then normal force should also have 0 torque or 0 moment. So then the net moment will be just by the friction force and then this force, okay? So for the usual convention, we take the torque that makes the object rotate counterclockwise to be positive. Okay, so then friction force, all right, and then this radius is 0.75. So this is 0.75, 0.75. So it's going to be the 0.75 times the friction force, okay, or it says F sub A, that's the friction force on point A, okay, it's going to be F static. All right. Now, for this pulling force of 30 Newton, you will pull this spool clockwise, rotate clockwise. So it's going to be negative. Clockwise be negative. Okay. So it's negative of the radius at the actional point or distance from x0 station to the actional point is 0.2 times the 30 newtons. Okay. All right. That should be equal to, so the net moment should be equal to the I times alpha. Okay, so I in this case or I times alpha, I is the 80. I should be equal to 80 times the radius, because this is, yeah, it tells us the radius of gyration. So m times kg, okay, times 0.3 squared. This is the I times alpha. Okay, now you can see here alpha is going in the clockwise direction, so you want to put the negative sign here. Okay, so then this should be the um, the moment equation about point G. Okay, so the first force clockwise, counterclockwise direction positive, clockwise direction negative, equals to the negative because the alpha is clockwise. Okay, any questions you guys have on this one before we move on to the next one? Okay, so if that's clear, then we'll check on the two attention quizzes here. Okay, so this one says a cylinder of 100 kilogram is suspended by this cable here. The moment equation about point A, what would that be? And then the equation that best represented non-slip assumption here. Okay, so let me open. I think the breakout rooms are open. You guys can rejoin it. Okay, so rejoin your breakout rooms and then work on this too. Okay, we'll come back in a few minutes to check on the solutions. All right, so you are all back. Let's take a look here. So you guys say, most of you guys say C and C. Okay, so the first one, so now this time it says this cylinder is rotating about, if it's for the moment the equation about point A. All right, so then we will be writing this in a different fashion. So moment on A is going to be, we are going to use this expression here, I about G times alpha plus M times of A of G times RG with respect to A. Okay, so if that's the case, then in this case, there will be just one external force that has the moment on the object, because for the, if you look at the free body diagram again, all right, so there'll be mg, there'll be tension T. All right, so these two forces will go through point A. So then distance for these two forces will be equal to 0, R for these two. Okay, so only this guy will have moment. Okay, the 10 newtons. So then it's going to be the 10 newtons times the distance to point A. So 3 times 10, okay, equals to I with respect to G will be 12, 1/12, M 100. Okay, the length will be 4 squared times alpha. Okay, so this is I of G times alpha plus the mass of 100. Acceleration at this point should be just in the x direction. Okay, because at this point the net force is in the x direction. Okay, so A G sub x. Okay, times 2. All right, 2 will be from this guy. All right, so this is this one. The correct answer is C on this one here. All right, on the second one, select the equation that best represent a non-slip assumption. Okay, so this is a separate question from the first one. So this is referring to if you have a rolling motion, if there's no slip. So which equation applies? Okay, so no slip limit means there's static friction. Okay, so B is not involved because it's talking about kinetic friction. So then either A or C, okay, that we should be looking at here. And then if none of this, then we can consider D. Okay, but let's take a look at A first. A says the friction force is going to be equal to lead. Okay, so that's not always true. Um, um, Occasionally, if you have the stream condition, that friction might be equal to that. But most of cases, the friction force should be less than this. Okay. C says Ag should be equal to R times alpha. That's right. Okay, we derived this in chapter 16 when we talk about relative motion. Okay, so this guy is correct. Okay, so it's C. All right, so we should take C as the correct answer here. Okay, questions you guys might have? All right. If not, then we do have some time for. We are not going through example today because there's some problem, some issue with the example provided by the publisher. So I don't like the example, but we'll just do a group problem solving today. Okay, so so this is the one. Okay, you guys are going to do. I'll give you guys about 10 minutes to work on this, and then at the end, a few minutes, we can take a quick look on the solution together. Okay, so again, go back to your breakout rooms. Okay, and then work on this as a group. Then we'll take a look at the solution later. Okay. All right, so I've forced to close on the breakout rooms as we are running close to the end time here. So basically, you'll start with the free body diagram here. Okay, so there's a free body diagram. You'll see that there's a weight on the object. There will be a normal force. There will be a friction force. Okay, so in this case, because the this concrete covered is not slipping, so then the friction force should be static friction. Okay, static friction should be pushing this guy forward in the forward direction. Okay, so three forces here indicated. For the kinetic diagram, so you will see that for the oscillation of the body, it's going to be horizontally to the right. And then this is for rotational oscillation, it's going to be in this counterclockwise direction. Okay, so if we set up the XY coordinate system as usual, like the um, X to be the horizontal, Y to be the vertical, then we can see for the equation of motion, the three equation of motions, we can write them up like this. So for the X direction, it's going to be equal to this guy, the M times this G, okay? So then the friction force is equal to M times A G in the X direction, okay? There will be no Y direction oscillation then. In y direction, normal force and weight will cancel out. Okay, so normal force is going to be that equal to the weight. For the moment equation, so this is point A over here. If you take that as your x rotation, then it's going to be I times g, okay, ig times alpha minus m, okay, a r, okay. So so this is so for the moment equation over here, because if you take A as your x rotation going through that point, so each force is going through A, so then summation of moment is going to be 0. Okay, so that will be just an alpha, I alpha, and then this is from the net force. Okay, so this is guys pulling it forward. This is going in that direction, so it's going to be negative. This is counterclockwise. This guy will pull it in the clockwise direction, so it's a negative. Okay. From here, we get the expression of alpha equal to 2g ag. Okay. So now we would need a second equation or another equation to solve for this, because there are two unknowns here. Now this is the only equation you have remaining. Okay, and then this is the so this is just gives you m. Okay, so you couldn't use that anyway anymore. But in this one, it's kind of so you have to use this guy. Okay, it's a little bit tricky here. You don't use the alpha equals to or the a equals to r times alpha. Okay, because you can see from here it doesn't apply that way. Okay, so this is not just a object rolling on a stationary ground. The track, it has an oscillation, so that we have to be careful. But we can use this guy because at this point this is stationary, so then this point will have the same oscillation as the track. Okay, so you can use this guy. So then it's an x and y component that, as we set up earlier in the previous chapter, you can check that. Okay, so at the end, you'll get a second equation from I, you'll get another equation from J direction, but you only need this guy, okay, to be paired up with this equation. Use these two equations, you can solve for the alpha and the A sub G, okay? So that's on that one. Any questions you guys might have for me at this moment?
What's
I hope
that thing on the bottom there? The
this guy
under
here.
the the bottom one.
Mm-hmm.
Is that a what?
AM. So this is normal direction of the oscillation. Okay.
All right, sweet. Thanks.
Yeah, we don't actually use this information. We are not looking for anything associated with the normal direction of oscillation at that point. Okay, so at that point, you should have a tangential direction, which is a horizontal direction. You should have a normal direction of oscillation. Okay, but we are not looking for this one at this moment, so we don't have to worry about that. Okay. Last thing I would like to mention is, so I forgot to mention this earlier. I posted the solutions to exam 3 on Moodle. Okay, so that's just one file, but it has the solutions to both versions of exam. You guys either have version A or version B of the exam. Okay, check on the numbers. You'll see which version you have. Okay, so if you have questions about solutions to the exam, you can also let me know. All right. So that will be it for today. I will see you guys on Wednesday. All right. Don't forget the homework thing is due tomorrow. Okay. See you guys on
Have a good
Wednesday.
day.
You too.
Yeah.
Thank you. Bye.
Bye.